Okay, before we start looking at magnetic fields and directions and calculations and all that, we got a little bit more theory. And what we're going to talk about is a theory called domain theory. Most modern physicists, and I've seen it on Big Bang Theory, where they say they're trying to find a monopole, or where they're trying to separate the North and the South Pole and only have one of them. But that is yet to be proved, and until then, we're going to stick with the domain theory, which has been around for quite some time, as it explains a lot of things of how magnets work and how things change with magnets. If they ever do invent the monopoles, or they find that to be true, then this whole domain theory may be wrong, but for the time being, we're gonna stick with it. So we've already talked about that if we take a magnet and break it apart, so we have a magnet that's a north and south pole. If we end up breaking it in half, so if we break it in half, we'll just get two magnets now, both having a north and south pole, and so on. So we could keep going smaller and smaller, and what we find is that we just keep getting smaller and smaller magnets. But if we take a chunk of magnet and we actually look under a microscope, scientists said what they actually see are what they call domains. So what that means is sort of imagine having a chunk of metal, a magnet, and if you looked inside, you'd sort of see these little, sort of almost like little strands of metallic fibers, or sort of like elements type of thing, or little hairs. So they're sort of about 1 millimeter long roughly, and if we get a magnet, what happens is all these little domains, which basically act as like a little mini magnet inside, they all tend to be working together, so they all sort of point the same way. So we'd have, the north part of the domain pointing one way, so we'd get we'd get our magnet in that case. So in this case, I guess if those were acting like magnets, this would be the south pole, this would be the north pole of the magnet, and so on. But the direction, or what type of pole it is, isn't really that important. We're just sort of worrying about what happens when they're lined up. So if you have a magnetic metal, basically what that means is all those domains are lined up and they're sort of working together. If it's a non-magnetic metal, what we would get is this diagram that's at the bottom of the page. So all the domains are sort of scattered randomly and pointing against each other and canceling out and so on. So the theory itself suggests that the reason these domains occur is because the electrons are spinning in orbit around the nucleuses. So if you have a whole bunch of these electrons spinning, they're basically inducing a mini magnetic field. So a whole bunch of electrons working together, we get a magnetic field to create. And if you have a whole bunch of those, you get a little domain. And if you have a whole bunch of domains in alignment, we end up getting a metallic object, ends up being a magnet. So in ferromagnetic materials, so anything like iron, cobalt, and so on, we can get those domains to align. And all we basically have to do is either put the metal on top of an existing magnet. So if you take a chunk of iron that's not magnetic and you place it on top of a strong magnet, what will happen is those domains that are scrambled, if it's not magnetic, will sort of be forced to line up. So we'll take these mixed up domains, get them pointing in the same direction, and then that'll change that metal into a magnet. And we can see that this actually works, right? If you take a magnet and you try to pick up paper clips, what we're basically doing is changing the domains in the paper clips to line up, turning them into little mini magnets temporarily, and then we can sort of connect a few of them together to sort of make a little bit of a chain. So the question then is, if you make something magnetic, how do we know if it's going to be a permanent magnet or a temporary? And basically the idea is, are the domains locked in place? So if you take a chunk of iron, and when we form it, if we lock those domains into place, then we'd say it's going to be a permanent magnet. And we call that hard iron. And the way to create it, basically, when they make the iron and it's liquid and they form it, they basically place it in a strong magnetic field to line up all those things in place, and then as the liquid hardens, they basically stay locked in place. That's why they call it hard iron. It happens as it hardens. If the domains can be moved around easily, so if we have a chunk of metal where the domains can be lined up if they're near a magnet, and as soon as we move the magnet, they get all scrambled up and point in different directions again, then we say that would just be a temporary magnet. So, and the name for that is, if we just create regular metal, we usually call it soft iron, that those domains are all scrambled up. And we use soft iron quite a bit when we're using electromagnets. So if you think of the big magnets that are used to pick up scrap metal and pick up cars and things like that, the idea is by themselves, they're just regular iron, nothing happens. We flick a switch, turn it into a magnet, it then is strong enough to pick up a car. We move it over someplace, turn it off, the car drops. So we'd be able to turn the magnets on or off, which is a valuable feature. So that's why we use a lot of soft iron for electromagnets. So one last thing with magnets, you may have seen it or by accident we see that we get magnets over time tend to weaken, and it's usually from them being dropped or banged around or whatever. So if you take a magnet and you drop it on the ground, when it hits the ground, we're basically shaking it up or bumping the electrons and the atoms. So if those electrons move around enough and speed up enough, what we can do is basically mess up the domains. So if they're not pointing all in the same direction anymore, it's no longer going to be a magnet. Or we can just take a magnet, bump them a little bit so that some of the domains move. It'll just become a weaker magnet. And one other thing that we can do to destroy a magnet is heat it up. If we get a magnet super hot, the heat, right, usually most particles speed up when they get hot, so the electrons start moving faster, they bump around, they change directions, the domains change, and then it's no longer going to be a magnet once that metal gets really hot. And just through experiments, we know that once we hit a certain temperature, it is impossible to make a magnet. So for example, iron, if we hit it about 770 degrees Celsius, you'll never be able to make a magnet. So they call that the Curie temperature, which was named after Madame Curie, who was a fairly famous French physicist. And that's all. We're going to get into some calculations and figuring out directions in our next lesson.